Let's talk about .NET assemblies. That's actually pretty cool because .NET assemblies are being used by malware a lot recently. So you definitely want to learn about .NET. You'll definitely want to learn about the tools being used for you to analyze malware, and definitely, first of all, to understand how the .NET assemblies work. Okay, so this is a kind of old view, but still useful, of what are all the suite of .NET in Microsoft, so that you can see that you can build websites, desktop applications, cloud applications, mobile applications, gaming, IoT. So it's a whole suite of different options for us now, thanks to .NET. And when we go into the details, what is a freaking beauty feature is that you can have multiple program languages as a source code, like Visual Basic, PowerShell, C++, C Sharp, JavaScript, J, F, J Sharp, F Sharp, many others. But at the end, all of those guys are going to be compiled into what is called an intermediate language in .NET, okay, which is like a bytecode. Think about it like an assembly code that understand all those guys, and this guy here in the middle is actually the same layer. It doesn't matter if you are built in these different languages. With the compiler, now you get into the bytecode, and at this point is essentially the same. Okay, then from here you can start calling also obviously class libraries like systemnet, reflection, security, so you can add those into this functionality. And then after that, you can call CLR, which is the command language runtime, which is basically this guy is going to be the bridge between what is called the managed code, which is this code above. It's called managed code because it's code that is not the actual source code. It's the source code that was managed by MSIL and the compiler, and it's kind of wrapping up in terms of protection and many other features. And that managed code is going to be taken by CLR, and from there is going to be run native code. And native code is actually the final program that is executed in the file system. You can also have from compiler on managed code, basically meaning you don't go into this layer and it's just straight into native code. Okay, you see here in the middle JIT compiler. This is just in time compiler, meaning that sometimes if you have code that you don't want to compile at the beginning, you can just leave it with some specific preprocessor instructions, and then these functions are going to be compiled in memory at runtime whenever they are used. That's very cool because then you don't need to compile everything. You just need to compile whatever is needed at memory, and that saves a lot of time and is more fast for programs to run because you don't need it to use it at the beginning. It has the trade-offs, obviously. Depends on what you want, but basically the JIT compiler is being used in memory to compile those that are not being used, that were not compiled before. Okay, so the assembly manifest is very important in .NET. It has all the different instructions from MC code. It can be stored either inside the PE file with MSIL code, or can be in standalone PE. But those are basically containing the elements of the assembly related to each other. It can have the assembly version, security identity, scope, result references, resources, and classes, right? So that's kind of the building process that a manifest can provide always for a DLL or multiple DLLs or files. It is the manifest with some of those instructions. Is always needed for .NET. It can also tells you which .NET version you want to run into when you execute your program. Another quick difference is that if you remember when we look at the executables in Windows, when you talk about .NET is actually the same format, exactly the same that I just described, but it has two new sections, which is called .NET Metadata Directory and .NET Directory Size. That's the new sections that you have in a .NET binary. But internally, you have the MC header, you have everything that we described in the Windows formats module. But additionally, it has all those two guys. And another thing very, very important is that the entry point of the .NET is a different entry point than a traditional executable. A Windows traditional executable, you will find your entry point following the P header as we described in the Windows binary module. But for .NET, you have a different entry point which comes down from the .NET directory. Okay, so normally you will find the entry point inside the .NET directory, which is like a second entry point of .NET binaries. You also have what is called metadata streams, which you can look at those like sections in a PE file, where you can have like strings, GUIs, blobs. Let me describe you a little bit about those. What those means. For example, this sharp and this tilde, this stores all the information of assembly metadata. This stores namespace and member names. This stores all user-defined strings. You know, this US defines all user-defined strings. That this guy, GUID stores GUIDs, blob stores pure binary data. Okay. Metadata tables. Each metadata table holds information about the elements of your assembly. Metadata enables self-describing files and cross-language inheritance. This is very important because these metadata tables, as it says here, it make it very, very compatible in cross-language. And you will see that in a second. Why? Because the metadata basically has like an index, and you can have a table name that describes what that means. So the code 0, for example, is a module. The code 4 means this is a field. The code 6, this is a method. 8 is a param. And then every single index has a meaning, and that makes it very, very portable. Very, very portable. Let's see an example of this. So imagine that we have here a program, and this program is called Hello HackDev, okay? And then you see here this 00, that's the table ID that we're calling here. So we have a table ID and an index ID. Table ID is in the left side, 00, and the index ID in the right side. So in this case, is 00 the table ID, in this case is 06, and in this case is 08. What is 00? Let's go back. 00, that means it's a module. 06 is a method. 08 is a member reference. Okay, module, method, member reference. So we have here a 00, it's a module. You see here module 00. 06 is a method. 01 is method 1. This guy here is 02. And this guy is a member ref 0A. And if you count all of these guys, 10 is 16. And that's why you have this. So you can see how this metadata influence these parsers, because this is a tool that is parsing the source code. And that's the reason it's able to understand this is a module, this is a parameter, this is a member reference, okay? And that make it portable and cross-language with Visual Basic, with C#, F#, and those guys. As I said before, right? Okay. If you look at the editor, MC code editor, you will see the same here. You see here the method. So the editor says, hey, this is a method. Why? It can see the 06 here, which is a method, and 01 because it's the first method. US, you remember, is a string. As you remember, it was a string. And 01, here is the first string of the program. Type ref is 01. And console, you don't believe me, this is 01. Let's go back. Oh, here, maybe it's here. Type ref, yeah, 01 is type ref. Okay. Now, What else? We have a member ref 0A and 10, which is write line. Okay. And then we have here 23, which is assembly ref, and 01 is mscorelib, which is basically means an external reference, and this reference is mscorelib, which is one of the main libraries from .NET. So as you can see, this is MSIL code, but all these metadata helps easily to understand by parsers those different tokens. Okay, let's see now how this whole thing runs in a glimpse. So first, you double click on an executable, .NET executable, that calls the CLR. The CLR has an internal virtual machine. It loads the managed code. Remember, this is managed code that was created with the compiler of .NET. That code goes into MSIL Bytecode, intermediate language. That triggers our compiler. Then the compiler says, hey, let me consult. And let me know if you want me to compile anything. It says to the MSIL code. Okay. Then it says, I'm going to go and convert into native code. But if you want me to run a function that has not been compiled before, I'm happy to call JIT, to just-in-time compiler, in order to convert it right in memory into native code. Okay, engine is the generation of this native code engine, and method cache is just to save this conversion so that you save time. So then in a glimpse, you load it from the beginning, get the MC code, you can consult the metadata, all those different tokens that we just described. It start parsing the different methods, and then if there is a method that has not been compiled, it calls JIT, compile it and run it. If it is already compiled, it doesn't call JIT, it just run it. And if it's already run, it calls method cached and it doesn't be converted again. That's pretty much it. Okay, and finally gets executed into the system. This is a great article. To be honest, maybe it doesn't exist anymore. Maybe you can find it in back in time machine or something like that. It was one of my favorites where I learned this whole description of PE's formats. So I highly recommend it. Hopefully you can find it. If not, there's plenty of information there. In summary, guys, so we talk about the process to build a binary, the whole process to compile it, link it, and execute it, and run it in memory. We talk about the formats of the Windows files, how the loader works from double clicking, loading the memory, and getting executed. And then we talk about .NET, the metadata of the .NET, the CLR component, and how that gets executed into memory. See you in the next one.